You probably started today by, doing a dozen calculations before you even finished your morning coffee.
Oh, absolutely. I know I did.
Right. Like you looked at the clock to figure out how many minutes of sleep you could still afford.
The most important calculation of the day, honest.
Exactly. Or maybe you estimated the volume of milk left in the carton just to see if it would cover a bowl of cereal.
Right, or mentally dividing the remaining fuel in your car by the distance of your commute.
Yes. Most of us go through our entire daily routine relying on this underlying machinery of mathematics without ever really looking at the engine itself.
We just take it for granted.
We totally do. We assume mathematics is this sprawling, like infinitely complicated encyclopedia of millions of independent, disconnected rules that we just had to memorize in grade school.
Just a giant list of chores, basically.
Exactly. But our deep dive today focuses on a text that completely strips that assumption away.
It really does. It blows the whole thing wide open.
It's wild. The entire chaotic, massive universe of mathematics, and I mean everything from figuring out a tip at a restaurant to like the most incredibly complex orbital mechanics, is actually held together by just 12 invisible, incredibly simple rules.
It completely reorients how you view the subject. I mean, we often treat mathematics as this collection of disjointed spells or magical incantations.
Right, like reciting a potion recipe.
Exactly. You memorize the quadratic formula, you memorize how to cross-multiply fractions, and you just sort of hope you apply the right spell at the right time.
But the source material for this discussion changes that entirely. We're looking at an excerpt from Chapter 1 of Michael Spivak's famous textbook, Calculus.
Specifically, the chapter titled Basic Properties of Numbers.
Yeah, and the mission of our deep dive today is to take those foundational principles and unpack them for you.
We're going to translate the formal logic of Spivak's text into plain, simple language.
Right, because we want this to be super beginner-friendly. We'll use everyday examples to show you how these 12 properties operate in your daily life.
We're essentially looking at the source code of reality here.
I love that phrase. And Spivak frames this beautifully. The overarching story we're telling today is about how mathematics achieves its flawless organization.
It's a story of taking something entirely familiar, like basic arithmetic, and condensing it into a tiny rule book.
A rule book that surprisingly governs absolutely everything.
To sort of visualize this, consider the architecture of a massive metropolis.
Okay, like a giant city.
Right. You look at a skyline and you see suspension bridges, skyscrapers, intricate subway systems, winding roads.
The complexity is completely overwhelming.
Exactly. But if you walk up to one of those skyscrapers and examine it really closely, you might discover that every single structure in this entire city is constructed from just 12 specific types of interlocking blocks.
Like Lego bricks.
Yes, exactly like Lego bricks. You cannot build a skyscraper without first understanding how those individual blocks snap together.
And Spivak organizes these 12 properties with that kind of deliberate architectural precision.
He really does. He starts with the simplest foundational blocks, which deal exclusively with addition.
So looking at section 1, the foundation of addition, this covers properties 1 through 4.
Right, and the text points out something about addition that feels so obvious, you almost miss its significance.
What's that?
Well, before even naming the first property, Spivak notes that human beings only ever add two numbers at a time.
Oh, wow. Yeah, I guess that's true.
It's a crucial observation about our cognitive limitations, like how we actually process operations.
Right. If someone hands you a grocery receipt with like 15 items on it, your brain doesn't compute all 15 values simultaneously in one giant flash of insight.
Nobody's brain does that.
Yeah.
You take the first two prices and you add them together.
Right.
You take that resulting sum and you add the third price to it. Then you take that new sum and add the fourth.
So addition is fundamentally a binary operation. It strictly operates on pairs of numbers.
Exactly. And that biological limitation brings us directly to property 1.
Which Spivak calls the associative law for addition.
Right. In its algebraic form, it states that A plus the group D plus C is equal to the group A plus B plus C.
So if we translate that into a real-world scenario, think about packing for a weekend trip.
Okay, a packing analogy. I like it.
Yeah. So you have your suitcase open on the bed, and you need to pack 3 categories of items. Let's say your shirts, your pants, and your socks.
The grouping of those items is exactly what Property 1 addresses.
Right. It does not matter if you place your shirts and your pants into the suitcase first and then toss the socks in afterward.
Or, alternatively, you could bundle your pants and socks together first, put them in, and then add the shirts on top.
Exactly. The sequence of how you grouped those items together doesn't alter the final physical reality at all. The total contents and the total weight of your luggage remain completely identical.
And this simple rule prevents massive mathematical ambiguity.
How so?
While Spivak highlights that because of Property 1, we can completely drop the parentheses when writing out an equation.
Oh, right. We can just write a plus B plus C.
Yes, and we know perfectly well what it means because the underlying structure guarantees the sum is identical regardless of where we might mentally place the parentheses.
It's like a built-in safety net.
Totally. And he offers a really fascinating detail to illustrate the power of this rule.
Which is?
If you have just 5 numbers to add together, there are actually 14 distinct ways you could group them using parentheses.
Wait, really? 14 different structural arrangements for just 5 numbers?
Yes. You could group the first 2, add the third, then group the final 2, and add those sums together.
Oh, I see.
Or you could group the middle 3, then add the ends. There are 14 unique logical paths.
But because of the associative law, every single one of those 14 paths converges on the exact same sum.
Exactly. This property allows us to write long strings of numbers with what Spivak beautifully calls a blithe disregard for the arrangement of parentheses.
A blithe disregard, I love that phrasing. Without this structural guarantee, mathematics would just, well, it would collapse into subjective interpretation.
It would be chaos. You and I could look at the expression 1 plus 2 plus 3 plus 4 plus 5 and arrive at entirely different totals simply based on our personal grouping preferences.
That would make splitting a restaurant bill among 5 friends an absolute nightmare.
A total disaster.
So the associative law guarantees that grouping doesn't matter. Now, the next 2 properties, property 2 and property 3, sort of operate as a pair, right?
They do. Property 2 is the additive identity, which states A plus 0 equals A.
Okay.
And property 3 is the existence of additive inverses, stating A plus negative A equals 0.
These 2 properties introduce concepts that took human civilization, like centuries, to fully formalize.
Oh, absolutely. The concept of nothingness and the concept of balance through opposites.
Right. Property 2 uniquely defines the number 0. 0 is the only entity in the entire mathematical universe that you can combine with another number through addition and cause absolutely no change.
A good way to visualize this is going for a walk.
Okay, let's hear it.
So property 2, the identity, is the equivalent of standing on a path and taking 0 steps forward.
You remain exactly at your starting coordinates.
Exactly. Now, property 3, the inverse, introduces the idea of undoing an action.
Right, like walking backward.
Yes. If you take 5 steps forward, which represents a positive value, and then you take 5 steps backward, representing your negative inverse, where do you end up?
You end up exactly at 0.
Right. Every magnitude has an equal and opposite magnitude that completely annihilates it, returning the system to a state of nothingness.
And that physical action of undoing leads to a conceptual shift in the text that, honestly, many people find super surprising.
The part about subtraction.
Yeah.
Yeah.
In primary school, we're taught 4 fundamental operations, right? Addition, subtraction, multiplication, and division.
But Spivak uses these first 3 properties to reveal that subtraction does not actually exist as an independent primary mathematical operation.
It's entirely a derived state. Subtraction is just an illusion created by the rules of addition.
Precisely. The text explicitly states that the symbol A minus B is merely an abbreviation.
It's just mathematical shorthand.
Exactly. It's shorthand for A plus negative B.
Yeah.
You are never actually taking away anything in a pure mathematical sense.
You are always adding.
Always adding. Specifically, you are adding an inverse.
So instead of thinking, I have a basket of 5 apples and I take away 3 apples,
Right.
the structural mathematics is actually saying, I have a collection of 5 positive apples and I am introducing a collection of 3 anti-apples.
Anti-apples, yes.
And they just cancel each other out.
That distinction is so necessary for the structure of algebra to hold together. Spivak demonstrates this by showing how we solve a rudimentary equation, like x plus 3 equals 5.
Right, we're often taught to just subtract 3 from both sides.
But what we are really doing is relying on the foundational blocks we just defined. We introduce the additive inverse, negative 3, to both sides of the equation.
So that gives us the group x plus 3 plus negative 3 equals 5 plus negative 3.
Exactly. Then we invoke property 1, the associative law, to shift our mental grouping.
Ah, so we turn the left side into x plus the group 3 plus -3.
And then property 3 kicks in, telling us that 3 plus -3 resolves to 0.
So now the equation is just x plus 0.
Which leaves property 2 to finish the job. It tells us that x plus 0 is simply x.
Wow. And on the right side, the addition of 5 plus -3 resolves to 2.
Exactly. The seemingly simple act of subtracting 3 is actually a rapid sequential deployment of 3 distinct foundational rules.
Seeing the underlying mechanics of such a simple equation really highlights how robust the system is. I mean, every single microstep is justified by a law.
It's airtight.
Hmm.
And that brings us to property 4, which is the commutative law for addition.
Which states that a plus b equals b plus a. The order in which you present the numbers does not change the outcome.
Right. While property 1 addressed the internal grouping of numbers, property 4 strictly addresses their sequence.
I think a morning coffee routine is the perfect illustration here.
Let's do it.
Okay, so if you pour your brewed coffee into a mug first and then pour in a splash of milk, the liquids combine to form a specific beverage.
A delicious beverage.
Exactly. But if you decide to pour the splash of milk into the empty mug first and then pour the hot coffee over it, the molecular combination is identical.
The sequence of addition does not alter the final product.
Not at all. That intuition holds up perfectly for addition, but it invites a really critical question that the text addresses.
The subtraction problem.
Yeah. If addition is commutative, meaning a plus b is identical to b plus a, why does subtraction fail this test? Why doesn't a minus b equal b minus a?
It's a great question, because if we just establish that subtraction is really just adding an inverse, it seems totally logical that it should follow the exact same sequential freedom as normal addition.
It seems logical, but Spivak clarifies the boundary. The expression a minus b only equals b minus a in the very specific scenario where a and b are the exact same number.
But the brilliant insight Spivak offers here is about the limitations of our current toolkit.
Right.
He points out that using only properties 1 through 4, we are utterly powerless to rigorously prove that a minus b does not generally equal b minus a.
Wait, really? We can't prove it yet?
Not with just those 4 rules. I mean, we all intuitively know that 5 minus 3 gives a different result than 3 minus 5.
Obviously. 2 versus -2.
But a mathematical feeling is not a mathematical proof. We are structurally limited at this stage of the text. To prove this inequality, we require properties that govern a completely different operation.
Oh, I see. We need tools from the multiplication toolkit to finish a proof about addition.
Exactly, which just highlights how intertwined these systems ultimately become.
So let's look at those multiplication tools. This brings us to section 2, the foundational rules for multiplication, which encompass properties 5 through 8.
Right, and the architecture of multiplication is deliberately designed to mirror the architecture of addition.
Like a parallel universe.
Exactly. Spivak notes that the basic properties of multiplication are so structurally similar to addition that they require minimal individual justification. They act as this perfect parallel.
We can see that mirror clearly in property 5 and property 8. Property 5 is the associative law for multiplication, stating that A times the group B times C equals the group A times B times C.
And property 8 is the commutative law, stating A times B equals B times A.
They enforce the exact same freedoms of grouping and sequence that we saw in addition, just applied to a new operation.
They do.
I use these properties constantly when cooking, actually, particularly when trying to scale a recipe up for a large gathering.
Oh, that's a perfect everyday example.
Right. Imagine you have a recipe designed to feed 2 people. Initially, you decide to double it to feed 4. Mathematically, you are multiplying all ingredients by 2.
Makes sense.
But later, you find out even more guests are arriving, so you need to triple that expanded recipe, so you multiply by 3.
So you took the original amount, multiplied it by 2, and then multiplied that entire result by 3.
Exactly. That is a practical application of associative grouping in multiplication.
Right. And thanks to properties 5 and 8, the mathematics guarantees that you could have simply multiplied the original recipe by 6 from the very beginning.
Or I could have chosen to triple the recipe first and then double that result.
Exactly. The sequence of your multipliers and how you group them in your head will not change the fact that you will end up with the exact same volume of food.
The mathematical integrity of the recipe holds firm, regardless of the order of operations.
So the parallel universe of multiplication holds steady, but the mirror begins to reflect something far more, philosophically complex when we reach property 6.
Ah, yes, property 6.
This is the multiplicative identity. It mirrors 0, the additive identity. For multiplication, the identity is the number 1.
Okay, so the property states that A times 1 equals A.
Right. Multiplying a magnitude by 1 leaves the magnitude entirely unchanged. However, Spivak includes a highly specific, seemingly obvious addendum to this rule.
He explicitly mandates that 1 does not equal 0. I have to admit, the first time I encountered that, it felt almost comical. It explicitly writes out 1 is not equal to 0. You naturally wonder why a brilliant mathematician writing an advanced calculus text feels the need to codify something a toddler understands.
It does feel absurd until you remember the rules of axiomatic architecture. We are constructing a logical universe from absolute scratch here.
Right.
If a rule or a constraint is not explicitly written down, it does not legally exist within that universe. Spivak explains that 1 not equal to 0 must be listed as a fundamental property because it is impossible to prove using any of the other properties we've established.
Wait, you can't prove that 1 and 0 are different.
Not without explicitly stating it. Consider the alternative. What if the entire mathematical universe consisted of a single solitary number? Just the number 0.
A universe of absolute nothingness.
In that universe, every single rule we have discussed so far would still function perfectly.
Really? Let's test that. The associative law.
0 plus the group 0 plus 0 equals the group 0 plus 0 plus 0 plus 0. It works.
The identity law.
0 plus 0 equals 0. It works. Even the multiplicative identity would hold true. A times 1 equals A would simply become 0 times 0 equals 0.
Oh, wow. So none of our foundational laws would break.
None of them. The system would be perfectly consistent, but entirely devoid of meaning or magnitude.
So by explicitly codifying that 1 cannot equal 0, we are forcing a second entity into existence. It's like the mathematical equivalent of the Big Bang.
That is such an excellent way to conceptualize it. It is an axiomatic demand that the universe must contain at least 2 distinct non-identical objects.
And that single constraint shatters the singularity of 0 and allows all subsequent complexity, magnitude, and geometry to unfold.
Exactly. It is a profound philosophical statement disguised as a trivial inequality.
Okay, so with the mathematical universe now populated, we need our inverses. Property 7 introduces multiplicative inverses.
It dictates that for every number, a that is not 0, there exists a corresponding number, designated as a to the power of -1, such that a multiplied by a inverse equals 1.
And here we encounter the second death of a primary operation.
Yes. Just as property 3 revealed subtraction to be an illusion, property 7 reveals that division is also a mathematical fiction.
Division is simply a shortcut for multiplication.
Exactly. Spivak points out that the symbol a divided by b is merely an abbreviation. It represents the number a multiplied by the inverse of b, or a times b inverse. You are never genuinely dividing. You are multiplying by a fractional inverse.
This structurally explains a trick I was taught in middle school math that I simply accepted on blind faith.
Oh, the fraction trick.
Yes. When tasked with dividing one fraction by another, the teacher told us to keep, change, flip.
Right. Keep the first fraction, change division to multiplication, flip the second fraction.
Keep the first fraction, change the division symbol to a multiplication symbol, and flip the second fraction upside down. I never understood the underlying logic until now.
It wasn't a magic trick to make the test easier.
No, it was the literal application of property 7. You eliminate the concept of division entirely by switching the operation to multiplication and utilizing the multiplicative inverse.
You were intuitively operating within the bounds of property 7 as a kid. But property 7 includes a very strict limitation, one that touches on perhaps the most famous anxiety in all of mathematics.
The restriction against 0.
Right. The property specifies that an inverse exists for every number except 0.
The fear of dividing by 0 is culturally pervasive. I mean, people joke that if you type it into a calculator, you'll open a black hole.
It's the ultimate math meme.
It really is. But stepping away from the hyperbole, what is the actual logical mechanism that prevents us from dividing by 0? Why can't mathematicians just invent a new symbol or a new number to represent the answer, the same way they invented imaginary numbers for the square roots of negatives?
That's a profound question. The prevention is baked into the fundamental definition of 0 itself. Remember that 0 possesses a unique absolute power in multiplication.
Right.
Any number, let's call it b, when multiplied by 0 results in 0. 0 times b equals 0. Now, property 7 requires that an inverse must be able to multiply with its original number to produce the number 1.
Okay, I see where this is going.
If we attempt to create an inverse for 0, let's tentatively call it zero inverse, we are demanding the existence of a magical number that can satisfy the equation 0 times 0 inverse equals 1.
But the very nature of zero is that it turns every multiplier into zero. It annihilates other magnitudes.
Precisely. There is no concept, no magnitude, no theoretical construct in existence that can survive multiplication by 0 and emerge on the other side as a 1.
It's impossible.
Because the concept of zero inverse contradicts the fundamental definition of 0, it is entirely meaningless. And since division is defined as multiplying by an inverse, attempting the expression a divided by 0 is an attempt to multiply a number by a logical paradox.
So it's not that the answer is too large to comprehend, it's that the question itself is structurally broken. It is a logical dead end.
Exactly. It's the equivalent of asking, how heavy is the color yellow?
Ha! The words form a sentence, but the combination of concepts has no valid meaning.
Exactly. And this careful segregation of 0 leads to a powerful tool in algebraic problem solving, which Spivak highlights. Because 0 has no multiplicative inverse, we derive the zero product property.
Which means?
We can conclusively state that if the product of two numbers is 0, if a times b equals 0, then we know with absolute structural certainty that either a must be 0 or b must be 0. There is no other mathematical path to arrive at 0 through multiplication.
This is the invisible engine behind solving polynomial equations, isn't it?
It is the bedrock of it. Spivak uses the equation x minus 1 times x minus 2 equals 0 as an example.
Right.
When a student sees that equation, they are taught to split it into two independent possibilities. Either x minus 1 equals 0 or x minus 2 equals 0.
Yeah.
That splitting action is not an arbitrary rule. It is a direct, unavoidable consequence of the fact that 0 lacks a multiplicative inverse.
Without property 7, we would have no logical justification to split that equation apart.
Not at all.
Okay, so we have established 4 rules for addition and 4 rules for multiplication. But right now, they're kind of operating in isolated silos.
Right. They haven't met yet.
Which brings us to section 3, the bridge between worlds. Property 9 is where the architecture truly integrates. Spivak calls this the distributive law.
It is expressed algebraically as a times the group B plus C equals A times D plus A times C.
If we view the previous rules as parallel tracks, property 9 is the switch that connects them.
It really is. It is the only property out of the 12 that forces the universe of addition and the universe of multiplication to interact. It dictates precisely how a multiplicative multiplier distributes its influence across an additive sum.
We promised earlier to tell a short story that illustrates how these laws take the chaos of mathematics and render it logical and organized. This is the perfect place for it.
I agree. Let's set the scene.
Imagine a 10-year-old student sitting in a classroom feeling totally overwhelmed by what seems like an endless list of arbitrary procedures.
We've all been there.
They are handed a multiplication problem, multiply 13 by 24. They have been trained to execute a very specific physical algorithm on paper. Stack the 13 on top of the 24, draw a horizontal line, multiply the 4 by the 3, write down the 2, carry the 1 to the next column.
Then you multiply the 4 by the 1, add the carried 1, write down the 5.
Then you must shift down a row, insert a 0 as a placeholder to shift the column alignment, and start the process again with the 2.
To a child, this feels like an arcane ritual. It's just a sequence of mechanical steps that must be performed blindly to summon the correct answer.
It feels like a magic trick. But Spivak's text pulls the curtain back on this ritual. The algorithm is not an arbitrary invention. It is merely a disguised mechanical application of property 9.
Let's break that down.
The problem 13 times 24 can be logically broken down. The number 24 is just 20 plus 4. So the expression is 13 times the group 20 plus 4.
And property 9 dictates that we distribute the multiplier.
Exactly. The equation expands into 13 times 20 plus 13 times 4.
Which perfectly mirrors the physical rows the student is writing on the paper.
Completely. The first part of the distribution, 13 times 4 equals 52. That is the exact number generated on the first row of the algorithm.
Right.
The second part, 13 times 20 equals 260. That is the number generated on the second row, with the placeholder 0 effectively acting as the multiplier of 10.
And finally, the algorithm tells you to add the two rows together.
Which is the final addition step of the distributive law. This story demonstrates that mathematics is not a collection of disconnected tricks. The most tedious multi-step algorithms condense down to the elegant application of this single law.
It really demystifies the mechanics of arithmetic. And property 9 is highly intuitive when mapped to a daily consumer scenario, too.
Like what?
Think about ordering fast food. You walk into a restaurant and want to purchase 3 combo meals for your group.
Okay, my fair kind of analogy.
Let's say a single combo meal consists of 1 burger and 1 order of fries. Mathematically, you are purchasing 3 times the grouped quantity of burger plus fries. Property 9 guarantees that this transaction is functionally and financially identical to purchasing 3 burgers independently, then purchasing 3 orders of fries independently, and combining them.
Ah, I see. So 3 times the group B plus F always equals 3 times B plus 3 times F. The total cost and the total calorie count will not deviate.
Exactly. It is a simple concept in reality, but it serves as the primary engine for algebraic proofs. Because Property 9 bridges addition and multiplication, Spivak uses it to prove concepts that we previously had to accept on intuition alone.
For example,
Earlier, we stated that a times 0 equals 0. We understood it conceptually, but we lacked the tools to prove it structurally. Property 9 provides that exact tool.
the text outlines this proof step by step, and it is a brilliant piece of deductive reasoning. How exactly do we use these foundational blocks to rigorously prove that multiplying by 0 results in 0?
We begin with a clever substitution based on the additive identity. We know that 0 plus 0 equals 0, so if we take any number a and multiply it by 0, we can represent that as a times 0. But we can also write the equation a times 0 plus a times 0. By utilizing Property 9, the distributive law, we can essentially pull the a out of both terms. This transforms the expression into a times the group 0 plus 0.
And since we know the value inside the parentheses, 0 plus 0 is simply 0, that entire side of the equation collapses back down to a times 0.
Correct. So we have established a new equation. A times 0 plus a times 0 equals a times 0.
Okay, I'm following.
From this point, we rely on Property 3, the additive inverses. We subtract the term a times 0 from both sides of the equation.
Okay.
On the left side, the addition of the inverse cancels out one of the terms, leaving us with a single a times 0. On the right side, subtracting a term from itself leaves us with exactly 0.
Therefore, the inevitable logical conclusion is a times 0 equals 0. We utilize the distributive bridge and the rules of addition to categorically prove a fundamental behavior of multiplication. That sequence of logic is incredibly satisfying.
It really is.
But Spivak does not stop there. He uses Property 9 to dismantle the most universally questioned rule in early mathematics.
Oh, the negative times a negative rule.
Yes. Why does multiplying a negative number by a negative number result in a positive number?
It is the classic dilemma that confounds students. Why should negative a times negative b equal positive a? Spivak makes a vital philosophical clarification here. He explains that mathematicians did not arbitrarily invent this rule because they felt it was aesthetically pleasing.
It wasn't just a stylistic choice.
No. If we desire properties 1 through 9 to remain true, if we want our architectural foundation to remain structurally sound without collapsing under contradictions, then this rule regarding negative numbers is absolutely forced upon us. It is an unavoidable consequence of the system we have built.
The text builds this proof in stages. Let's walk through the logic. Spivak first establishes a stepping stone, proving that multiplying a negative by a positive results in a negative.
Specifically that negative a times b equals negative ab.
Right. How does he start?
He sets up an equation designed to exploit the distributive law. He writes, negative a times b plus a times b. By applying Property 9 in reverse, we factor out the common multiplier, b. This leaves us with b times the group negative a plus a.
The expression inside the parentheses, negative a plus a, is a number added to its own inverse. Property 3 dictates that this resolves to 0.
Exactly. So the equation simplifies to b times 0, and based on the proof we just completed moments ago, we know b times 0 equals 0.
Let me summarize where we are. The equation is now negative a times b plus a times b equals 0. We have two terms that sum to 0.
Right.
If we isolate negative a times b by moving the a times b to the opposite side, which we do by adding its inverse, negative a, we reach the conclusion. Negative a times b equals negative ab, and negative times a positive is definitively a negative.
The stepping stone is secure.
So how do we leap from there to 2 negative?
We utilize the exact same structural maneuver, but we substitute a negative b into the framework. We set up a new equation, negative a times negative b plus negative ab. We just proved in our stepping stone that negative ab is functionally equivalent to negative a times positive b. So we substitute that equivalent value into our equation. The equation now reads negative a times negative b plus negative a times positive b.
I can see the architecture aligning again. Both of those terms share a common multiplier. the negative a. We deploy the distributive law once more to factor that negative a out.
Right.
The expression transforms into negative a times the group negative b plus b.
And once again, the expression trapped inside the parentheses, negative b plus b, is a number and its inverse. It resolves to 0. The entire expression simplifies to negative a times 0, which, as we know, is 0.
This is remarkable. The massive complex equation simplifies down to negative a times negative b plus negative ab equals 0.
And then,
To isolate the first term, we simply move the negative ab to the right side of the equation by adding a positive ab. And we are left with the final inescapable truth: negative a times negative b equals positive ab.
a negative times a negative equals a positive.
The logic literally forces our hand.
Yes. If you attempt to construct an alternate mathematical universe where a negative multiplied by a negative remains a negative, you will inevitably shatter the distributive law.
You'd break the bridge.
You will sever the bridge between addition and multiplication, and the entire logical framework of algebra will disintegrate into contradictions. The rule is not a choice. It is the load-bearing pillar of consistency.
Understanding that proof changes how you view the subject. It replaces rote memorization with a real appreciation for structural integrity.
It really does.
However, as robust as properties 1 through 9 are, they contain a massive blind spot. We have built an incredible system for manipulating symbols and balancing equations, but we have absolutely no way to determine magnitude.
Right, we don't know which numbers are larger, which are smaller, or what distance even means.
Which brings us to Section 4, bringing order to the universe. Properties 10 through 12.
Returning to our architectural analogy, properties 1 through 9 tell us exactly how the concrete blocks connect together, but they cannot tell us which skyscraper is taller.
To establish scale, magnitude, and direction, Spivak introduces the concept of a collection of numbers designated as p, representing all positive numbers. This brings us to the rules of inequalities.
Property 10 is formally known as the trichotomy law.
Which sounds super intimidating.
It does. While the name sounds intimidating, the concept is universally understood by anyone who has ever managed a budget.
Very true.
The trichotomy law dictates that for every single number a that exists, one, and strictly only one, of 3 conditions must be true. The number a is 0, the number a belongs to the positive collection p, or its inverse, negative a, belongs to the positive collection p.
And if the inverse negative a is positive, that inherently defines the original number as negative.
Exactly. In simpler terms, a magnitude must be 0, positive, or negative. It cannot occupy multiple states simultaneously, and it cannot exist outside of these 3 states.
This is the mathematical reality of a bank account balance.
Let's hear it.
At any precise moment in time, your financial state falls into exactly one of 3 categories. You might be perfectly broke, meaning your balance is exactly 0.
Right.
You might be in the black, meaning your balance is a positive magnitude. Or you might be in the red, overdrawn, meaning your balance is a negative magnitude. There is no mystical 4th state of personal finance. You are 0, positive, or negative.
Well said. Having established the boundaries of positive numbers, properties 11 and 12 introduce the concept of closure.
Property 11 states that the sum of 2 positive numbers will inevitably be a positive number.
And property 12 states that the product of 2 positive numbers will inevitably be a positive number. Adding positives maintains positivity. Multiplying positives maintains positivity.
Those rules feel incredibly intuitive. A positive plus a positive is a positive. But Spivak deploys these intuitive rules to mathematically prove a universal truth that governs geometry and calculus.
Ah, yes. The fact that squares are inherently positive.
Right. How does he prove that?
The proof relies on analyzing the available cases. Let us take any non-zero number, a. By the trichotomy law, it must be either positive or negative.
Okay.
We evaluate the first case. A is positive. If we square it, we are multiplying the times a. Property 12, closure under multiplication, dictates that a positive multiplied by a positive yields a positive. Therefore, a squared is positive.
That aligns with basic arithmetic. 4 multiplied by 4 is 16, which is positive.
No, we evaluate the second case. A is negative. By definition, if a is negative, its inverse negative a must be positive.
Right.
From the square of a, we multiply it times a. Based on the proof we explored earlier regarding negative multiplication, we know that multiplying 2 negatives is equivalent to multiplying their positive inverses. So negative times negative a yields the exact same result as a times a.
Oh, I see.
Since negative a is a positive number, multiplying it by itself must result in a positive number according to property 12. Therefore, even when the original number is negative, its square, a squared, remains strictly positive.
The act of squaring mathematically obliterates any negative value. The result is forever anchored in the positive domain.
It is.
And Spivak uses this exact mechanism to definitively prove that the number 1 is greater than 0.
Yes, he notes the simple fact that 1 is equal to 1 squared. Since 1 is the square of a non-zero number, and we just proved that all non-zero squares are positive, 1 must be positive. Therefore, 1 is fundamentally greater than 0.
This is where the text introduces a concept that feels almost like science fiction to me.
Problem 25.
Yes. We spent the first half of this discussion establishing that 1 not equal to 0 is an axiomatic necessity to prevent the universe from collapsing into nothingness. We assumed it was obvious. But Spivak uses a specific exercise, problem 25 in the text, to demonstrate why properties 10, 11, and 12, the rules of inequalities, are not just redundant statements of the obvious.
They are the essential tether that binds pure mathematical logic to physical reality.
Exactly. Spivak introduces a theoretical construct known as a binary math table.
This thought experiment is crucial for understanding the limits of pure algebraic structure. Imagine an alternative mathematical universe. In this binary universe, there are only 2 digits in existence, 0 and 1.
Okay.
The rules of addition in this strange reality are defined as follows. 0 plus 0 equals 0, plus 1 equals 1, 1 plus 0 equals 1, and most jarringly, 1 plus 1 equals 0.
The idea that 1 plus 1 equals 0 fundamentally contradicts every instinct we have about accumulation.
It does.
It means taking a step forward and then taking another step forward magically teleports you back to your starting position.
It defies physical intuition entirely. Yet, here is the terrifying brilliance of Spivak's observation.
Lay it on us.
If you take this bizarre binary system where 1 plus 1 equals 0 and you rigorously test it against properties 1 through 9, it passes every single metric perfectly.
Wait, really?
Yes. The associative law functions, the commutative law functions. Even the distributive bridge operates without generating a single logical contradiction.
You are saying that the first 9 rules of mathematics, the foundation of all algebra, are entirely capable of describing a glitching, looping universe where accumulating 2 items results in having nothing at all.
Yes. Properties 1 through 9 are purely structural mechanisms. They dictate the grammar of shifting symbols and balancing equations, but they are entirely devoid of physical magnitude. They have no anchor to the concepts of larger, smaller, or distance.
That's wild.
It is only when we integrate properties 10, 11, and 12, the laws of inequalities and positive numbers, that we permanently anchor mathematics in the physical reality we inhabit.
Because we utilize inequalities to definitively prove that 1 is greater than 0, we know 1 is a positive number.
Exactly. By property 11, closure under addition, adding 2 positive numbers must yield another positive number. Therefore, 1 plus 1 must be positive. And if it is positive, the trichotomy law guarantees it cannot possibly be 0.
The inequalities are the safeguard. They are the physical constraints that prevent our logical equations from describing nonsense. They give permanent shape and weight to our foundational blocks.
They really do. And once magnitude and physical order are formally established by the inequalities, we can finally begin to describe space. This brings us to section 5, the absolute value and triangle inequality.
We are transitioning from the pure manipulation of numbers into the foundational concepts of geometry and spatial reasoning. The text formally defines absolute value, denoted by 2 vertical bars around a number, absolute value of A, by analyzing conditional cases.
Essentially, absolute value acts as a pure distance function.
Right. If a number A is positive or 0, its absolute value is simply itself. Absolute value of A equals A. But if the number A is negative, its absolute value is defined as its inverse, negative A, which effectively flips the magnitude back to a positive state.
The absolute value measures how far a number exists from 0 on a number line, entirely discarding the concept of direction.
It isolates magnitude. Whether an object travels 5 miles due north or 5 miles due south, the absolute value of its displacement remains simply 5 miles.
And this definition of distance leads directly into Theorem 1 of the text, universally known as the triangle inequality.
Which is huge.
It's one of the most vital theorems in all of mathematics, forming the basis for advanced topology and calculus. The theorem dictates that the absolute value of the sum of 2 numbers, absolute value of A plus B, is fundamentally less than or equal to the sum of their individual absolute values, absolute value of A plus absolute value of B.
The theorem establishes the mathematical limits of efficiency and distance. Let's contextualize this with a daily navigation scenario.
Always helpful.
Imagine point A is your house. Point B is the local grocery store. Point C is your gym. The mathematical expression absolute value of A plus B represents the absolute most direct straight line path from your house to the gym,
Is the path a bird would fly.
the optimized route. Conversely, the expression absolute value of A plus absolute value of B represents a path with a detour. It is the distance of walking from your house to the grocery store, stopping there, and then walking from the grocery store to the gym. The triangle inequality mathematically proved that the direct path will always be shorter than, or at the absolute most, equal to the length of the detoured path. Taking a detour can never decrease your total travel distance.
The spatial analogy resonates perfectly with physical reality. But the rigor of mathematics demands that we prove this spatial truth using only the numerical properties we have painstakingly defined.
Right, no maps allowed, just the 12 rules.
Exactly. Spivak presents two distinct methods for proving the triangle inequality, offering a profound contrast in mathematical problem solving.
He outlines a brute force method and then an elegant method.
The brute force method relies on exhaustively analyzing every possible case. Because absolute value behaves differently depending on whether a number is positive or negative, a complete proof must test every combination.
Which sounds tedious.
It is. You must algebraically evaluate case 1, where both A and B are positive. In case 2, A is positive, but B is negative. Case 3, A is negative, B is positive. And finally, case 4. Both A and B are negative.
Oh, wow.
You meticulously grind through the algebraic substitutions for each scenario, proving the inequality holds in all 4 separate universes. The logic is sound, but the process is highly tedious and mechanical.
It is effective, but it lacks grace. Spivak then reveals the elegant alternative.
The elegant proof leverages the powerful tool we established during our discussion of inequalities, the inherent positivity of squares.
Okay, how does that work?
Spivak observes a simple truth. The absolute value of a number, squared, is functionally identical to the original number squared, a squared. The physical act of squaring automatically annihilates any negative sign, perfectly mimicking the function of the absolute value bars. Recognizing this overlap, the proof suggests squaring both sides of the inequality.
By squaring the expressions, you analyze the square of the absolute value of A plus B in relation to the square of the absolute value of A plus the absolute value of B.
Precisely. When you expand both of those squared expressions using the distributive law, our essential bridge, the algebra simplifies rapidly. The squares handle the positive and negative signs automatically, entirely bypassing the need to analyze 4 separate cases.
That's so much faster.
The mechanical tediousness evaporates, leaving a highly refined, straightforward proof that the absolute value of A plus B must be less than or equal to the absolute value of A plus the absolute value of B.
And the text also specifies the singular condition for equality, right?
It does. The direct path is only equal to the detoured path if both numbers share the exact same sign. Returning to your navigation analogy, this equality only occurs if the grocery store is located perfectly and exactly on the straight line path between your house and the gym.
Any deviation from that perfect alignment guarantees that the sum of the detours will exceed the direct route. That theorem represents the culmination of this chapter's journey. We began by establishing rules for how to group numbers together in simple addition, and we steadily built an architectural framework robust enough to mathematically prove the fundamental laws of physical space and distance.
It is a remarkable progression of pure logic. We have traced the sequence from basic counting to the
mathematics. Every algorithm you struggled to memorize, every negative sign you forgot to carry on a high school exam, every confusing fraction you had to cross-multiply, and we have condensed that chaotic universe down into a highly organized, airtight foundation consisting of exactly 12 properties.
Just 12 rules.
4 foundational blocks for addition, 4 foundational blocks for multiplication, 1 critical bridge, the distributive law forcing them to interact, and 3 rules of inequality to anchor the entire structure to physical reality and magnitude.
When you understand those 12 components, mathematics ceases to be a disparate collection of arbitrary laws. It becomes a unified system.
The ultimate takeaway for our listeners is a profound shift in perspective. The next time you find yourself balancing a spreadsheet, scaling a recipe, or calculating a distance, realize that you are not executing a random trick. You are interacting with these 12 foundational rules.
They are the invisible machinery operating behind every calculation you will ever perform.
It is an empowering realization. But this exploration of Spivak's text contains a final, philosophical provocation that fundamentally challenges everything we have just established.
It really does leave you thinking. After spending all this time meticulously defining these laws, the text offers a conclusion that is entirely unexpected.
What does he say?
Throughout this discussion, we have meticulously detailed the behavior of numbers. We've constructed an unshakable fortress of logic, demonstrating precisely how numbers interact when subjected to addition, multiplication, and spatial measurement. Yet, in the concluding thoughts of this chapter, Spivak admits something remarkably humbling.
Which is?
Despite outlining these 12 axiomatic laws, we still lack a fundamental understanding of what numbers actually are.
Wait, what? We spent this entire deep dive defining them.
No, we defined their actions. We wrote the rule book for the game they play. But we have not defined the nature of the pieces on the board. Spivak acknowledges that the true philosophical definition of a number remains elusive at this stage. We treat them as familiar, tangible objects, we count apples, we measure miles, but we have not mathematically justified their inherent existence.
That concept is deeply unsettling. If all of modern engineering, architecture, calculus, and physics relies entirely on a description of the behavior of numbers based on 12 rules, what physical or philosophical reality are these numbers actually describing?
It's the ultimate question.
Are numbers merely a human invention, a linguistic tool we created to make sense of our environment? Or are they a structural, immutable reality of the universe that human beings merely stumbled upon and discovered?
We have mapped the architecture perfectly. We know exactly how the blocks interlock, but we have absolutely no idea what substance the blocks are made of.
That is the thought we leave you with today. The next time you look at a receipt or check a speedometer, pause to consider the philosophical mystery you are interacting with. You know the 12 rules that govern them, but the true identity of numbers remains one of the most profound unanswered questions in human thought. Keep questioning the foundations of the systems around you, and keep searching for the underlying structure hidden in plain sight.